This is our third session in our series of videos about EMC emission testing. In the previous session, we explained some of the features of the equipment we shall be using. In this session, we will show a typical setup and explain how to optimize the settings on our analyzer and to take our first results. So here is our test setup. Our product in this case is a table lamp. So this is our EUT. This is wired to an LASN or a LISN, which is bolted down to the ground plane, and the output from the LISN goes to our preselector, and from there it goes up to our analyzer, and the analyzer in turn is connected to our PC. Here is a close-up of our LISN. As you can see, it's bolted to the ground plane. It has two outputs, one for live and one for neutral. Now we can look at the product. It's a table lamp, touch controlled, off, 3 settings, and off again. Just quickly check our instrumentation again. The little blue box in front of the preselector is the preamplifier that goes between there and the analyzer. Now we can look at the software, start up our application, and what we receive next is the plotting screen. Typical Windows application. You can see the usual menu across the top, and the red buttons are our action buttons. First thing we need to do is to set the frequency range of interest, which is 9 kHz to 30 MHz, and set the input device, which in this case is going to be the LISN. Default LISN is the one we're using at the moment. And next set the fact that we have a preamplifier in circuit. This is a 30 dB preamplifier. And finally, we need to set the attenuator level. If this is not set correctly, we run the risk of overloading the analyzer and displaying distorted results. To understand why, I will use an analogy based on the effects of the tide on a rocky coastline. And the rocks represent our emissions spectrum. The level of the water represents our baseline. Because the tide is in, many of the low-level rocks are out of sight. We cannot see them. They're still there, but they're hidden from view. Now our analyzer, like all other analyzers, has so much dynamic range. The dynamic range dictates the minimum level we can see and the maximum level we can see. So our signals need to reside in this window. We cannot change the height of this window, but we can move it using the attenuator. Now at the current setting, our spectrum would look just like this. So much of the lower level signals is lost from view. Going back to our ocean view, we can now reduce the level of water. This is the same as reducing the amount of attenuation. It makes our analyzer more sensitive. If we look at the spectrum now, it would look like this, whereas before, with maximum attenuation, we saw this, where much of the lower level signal was lost to view. Going back to the ocean view, we can continue to reduce the attenuation, making our analyzer more sensitive, but here we run into a problem, because now this high energy signal at the left-hand side has exceeded the dynamic range of the analyzer. The analyzer cannot plot this information, so it gets distributed to other parts of the spectrum, producing a false result. Now this result would look like a perfectly good result if we didn't know any better. The problem is that this false result may cause a problem with the limits. So here we would apparently fail a product when actually it's a perfectly good product. So we need a technique to ensure that we don't cause this problem. We need to be able to ensure that we optimize the setting of the attenuator, and the way we do this is to go through the same series of steps that we've just been through. So if we go back to our ocean view, here we are with maximum attenuation, and we gradually reduce the attenuation, checking each time that the visible spectrum has not changed. We come to a point where the spectrum may suddenly change. At this point we've gone one step too far, and so what we do is go back one step, and that will be our optimum setting. So now let's return to the analyzer screen and run through the same procedure. We first select the highest attenuation level, 30 dBs. Just for confirmation, we show the input device in this area here. So we are now ready to make our first scan. Click on single sweep and off we go. Note how the frequency currently being measured is shown here, and the measurement settings of RBW, dwell time and frequency step are also shown in this area here. We have speeded up the video to save time here. As we approach 150 kHz, note how the scan settings change. As we are now basically running along the baseline, I'll stop the scan, store that result on screen, and select the next lowest attenuator setting. We'll start the scan again. Note how the vertical scaling matched the new setting of the attenuator automatically. And note how we can now see below the baseline we had before. This result looks pretty much as it were, so I'll stop that, store that, repeat the procedure again, and start again. Again, the result is very similar, so we repeat the procedure again, this time selecting 0 dB attenuation, and start again. Note that this time we have a red indication on the left hand side and a red band under the scan. This indicates that we may have overload problems. Although the scan seems okay in this area, we clearly have distortion. So I'm going to go for the 10 dB attenuation level and use this for subsequent measurements. I'll now select the limit, 55015, remains conducted, and we can now see we have issues with compliance in this area here. Our results are clearly over the limits, so further analysis is required. This full analysis will be the subject of our next session.